For the March 23rd lecture on arithmetic sequences. Our goal for today is to be able to identify and continue arithmetic sequences. Why are we doing this? Well, one big reason is that if we apply the rules of algebra here, we can take an arithmetic sequence and find really distant terms in that sequence without having to write down every single term before it. We can ask things like, what is the 100th term of this sequence? And I'll tell you all what a sequence is very shortly. So what you should be doing with this lecture video, if you haven't already, pause this video, get out your notes, and put today's date at the top. If you brought a textbook home, you can follow along on page 398. But I'm not going to be referencing any textbook problems. I'm just going to be doing the problems that are in this slideshow. So that would be just for you to see more examples of problems. All right, so the first question is, what is a sequence? And this is how I would define a sequence, and this is how you should write it in your notes. It's a list of numbers that follows a rule of some sort. And depending on what that rule is, it might be an arithmetic sequence, it might be geometric. I'll tell you what all of these things are very soon. So a list of numbers that follows a rule. So here we see an example of a sequence, 3, 5, 7, 9. These dots here means that it goes on forever. And each term, element, or member in that sequence gets identified by its position. So the very first number is the first term, then the second term, then the third term. Just have that definition written down. So notation for a sequence. So for a sequence, we label the whole sequence like this, A sub n. So that's a subscript. And this here, the subscript, tells us where in the sequence we are. So for example, if I have a sub 3, this is the third term in the sequence A sub n. All right, and if we need to be doing a problem with multiple sequences, we might have B sub n and C sub n, or S sub n is pretty common with sequences. All right, so what does it mean to be arithmetic? Today's lesson is all about arithmetic sequences. Well, here we've got two examples of two arithmetic sequences. 2, 8, 14, 20, 26, 50, 45, 40, 35, 30. What is similar about these? So they increase / decrease by a fixed amount. That's what we see here, plus 6, plus 6, plus 6, plus 6. So it's a fixed amount that is being added. And we could say here the -5 is being added, and that's why it's going down. So if you add a -5, it's the same as subtracting 5. But we'll just say it's always being added, but if you want a sequence to decrease, just add a negative number. So what does it mean for a sequence to be arithmetic? It has to increase or decrease by a fixed amount that is being added. So here we see another arithmetic sequence, -6, -1, 8, 15, 22. Here, to get from one term to the next, we add 7. But there's also another type of sequence called a geometric sequence. This is changing by a fixed amount, but it's multiplying. 2, 4, 8, 16, 32. We're multiplying by 2 each time. So that's not arithmetic. It's not adding the same amount each time. It's multiplying by the same amount each time. So here, copy down sequence number 1 and then answer the question, is it arithmetic? Well, let's see. To get from 23 to 24, I added 4. Then I added 4 again. Then I add 4 again. So I'm adding a fixed amount. So yes, this one is arithmetic. Let's look at this one here. What did I have to add to -3 to get to -12? Well, I had to add a -9. So then I went down to -12. To get from -12 to -42, I've got to add a -36. Well, this is not a fixed amount. So we'll say no, this is not arithmetic. It's not a fixed amount. But let's check and see if it's geometric. How do I get from -3 to -12? I multiply by 4. Let's see if that will keep working. Yep, times 4 gets me to that number, times 4 gets me to this number. So we can say, no, it's not arithmetic, and further, it is geometric. But it is possible for a sequence to be neither arithmetic nor geometric. It can just be some other rule that's not multiplying or adding based. All right, what is the common difference? Another vocab word for you, it's just how much an arithmetic sequence changes by. So we see in this example here, the common difference is 2 because we are adding 2 each time. If we were subtracting 2, then it would be a -2. So here we've got just another sequence that we know to be arithmetic, but what is the common difference? A foolproof way to find the common difference is to say that D, our common difference, equals a sub 2 minus a sub 1. So this is common difference. This is our second term. We're going to be subtracting our first term. So this is kind of helpful when the numbers are kind of big or you're not sure if it's positive or negative. In this one here, a sub 1 would be 22, a sub 2 would be 8. It would be -8 minus 22 equals -30. So D equals -30. So if you weren't sure if it was a positive 30 or a -30, we do the formula. We can confirm that it's a -30 each time. And then double check with terms further down. If I add another -30 here, do I get to -38? What about here? If I subtract 30 or add a -30, I get down to -68. Checks out. All right. So once you found that common difference, you can use it to find further out terms in your sequence just by repeating the process of adding it. So this one we are subtracting 4 each time. So just keep subtracting 4. We go 10, 6, 2. That circle. All right. What about this one here? Well, here I'm not sure if it's positive 10, -10. So I do -42 minus a -32. That's the same as -42 plus 32 equals a -10. And now I can see, oh yeah, it is a -10 each time. So I continue to subtract 10, I get -72, -82, -92. All right. Now we can put all of this together into a formula that gives us the nth term in any sequence. If we use this form here, which is called our explicit formula, just pause the video, copy it down. Now let's put it to use. All right, so what's the explicit formula of this sequence here? 40, 35, 30, 25. So to get to any a sub n, we can start with our first term, a sub 1, and add to it multiples of our difference equal to n minus 1. Let me double check I wrote that down correctly. Yeah, they put the d at the end. I think it makes more sense to me as a coefficient like that. So let's fill in what we can see. We can see a sub 1 is 40, so 40 goes in right there. Plus our common difference. What is our common difference? That is a minus 5 each time, so minus 5. And then n just stays as an n. That's our input variable. All right, now this can be simplified. So a sub n equals 40 plus negative 5 times n minus 1. We're going to distribute that negative 5. A sub n equals 40 minus 5n plus 5. Negative times a negative is a positive. Combine like terms here. And normally, for whatever reason, the 5 is normally brought to the front instead of bringing the 40 to the end. And so the constant goes first. A sub n equals 45 minus 5n. This will give us any term. We can double check it. Here our fourth term, a sub 4, should equal 25, so I'm going to plug in a 4 here. Negative 5 times 4 is negative 20. 45 minus 20 is 25. All right, let's try it with this one over here. A sub 1 is negative 14. Our common difference is we are adding 7. You do subtraction to double check that. And we'll get that a sub n equals negative 14 plus 7 times n minus 1, and then just simplify from there. Bring that negative 7 in front, negative 21 plus 7n. All right. Can we use the explicit formula to then find a more distant term, like the 52nd term? I think that we can. I'm just going to take a quick pause here, be right back.